In chapter 15, we've talked about acids. We've talked about strong acids, we've talked about weak acids, how to find their pHs. We're now going to talk about strong bases and also weak bases. So the stronger the base, the more willing that it is to accept H+. And so for ionic bases, things that we're already familiar with, like sodium hydroxide, calcium hydroxide, basically they dissociate 100%. They're strong electrolytes. They break up into the cation and the hydroxide. And if it is something like calcium hydroxide, where there's more than one OH group, it completely dissociates in one step, breaks apart into the Ca2+ and 2 OH minuses. So now just to remind ourselves on how to calculate pH, I'm going to ask you to pause the video and see if you can calculate the pH for our strong acid, HCl, and think about how you would calculate the pH for our strong base, calcium hydroxide. For HCl, we know that our H3O plus concentration is equal to that of the acid. And so to find the pH, it's just a matter of taking the negative log of this concentration. And we can find that in this case, it is 2.70. Now, when we want to find the pH of our calcium hydroxide, we're still going to have to think about, in this case, we have to think about the hydroxide concentration. So our hydroxide concentration is equal to 2 times the concentration of the base. Now, why is it 2 times? It's 2 times the concentration because of our subscript. And so in this case, our concentration would be 0.003 molar. We can find our pOH by taking the negative log of this concentration, which is going to give us an answer of 2.52. Now, how do we find pH? This is pOH. So pH is going to be equal to 14 minus our pOH. So pH plus pOH is equal to 14. So 14 minus 2.52, and our pH equals 11.48. And you can ask yourself, does that make sense? Well, it's a basic solution, and so we have a pH that's greater than 7, and that makes sense. Now, weak bases, only a small fraction of the molecules are going to accept that hydrogen. Just like weak acids, only a portion of them give off hydrogen. For weak bases, only a portion of them accept the hydrogen. So most of them are not taking that additional hydrogen from the water. So generally less than 1% ionize. And so we have to find our equilibrium concentrations in order to solve for the pH or the pOH of a weak base, similar to what we've already done for the pH of our weak acid. Now, because we're dealing with a base, we're looking at a base ionization constant. This is very similar to what we've already seen for Ka, except now because we're talking about a base, we call it the Kb. And it is still measuring the equilibrium constant. The B is for base. And it's still products. So our base plus the hydrogen, which is our product, times the hydroxide divided by the original concentration of the base. And the larger our Kb, the stronger our base is. There are lots of common bases. Some of them you're familiar with, some of them you aren't. So carbonate ion, and this always needs to be paired with a positive cation, but the cation doesn't contribute to our pH. Bicarbonate, so this is what is made, this is baking soda. Sodium bicarbonate is baking soda. It is also basic. And then you'll notice some of the other ones contain nitrogen. So lots of nitrogen containing compounds are weak bases. And we have a range of Kb values for these bases. And the reason that the nitrogen containing compounds are bases is because they have a lone pair that is able to accept that H plus that is given off. So let's try an example. Got ammonia, got 0.1 molar solution of ammonia, and we want to find its pH. So the very first thing that we're going to do is we are going to set up an ice table. So we're going to start with writing our reaction. And again, water won't be included in the ice table because it's a liquid. But just to make our reaction balance, these first few times I'm going to write the water. I write our ice table. So our initial concentration of ammonia is 0.1 molar. And our ammonium and our hydroxide when we first start are going to be 0. Our change in ammonia is going to be minus X. And for our products, it's going to be plus X. We add our columns down to get our concentration or what our expression is at equilibrium. Now I've been kind of skipping this step so far, but if we want to double check to see if we can ignore our X, we can compare that initial concentration just like we did with acids when we were still in class. We can compare it to our Kb value and see. So our book says if it's larger than 250, we can ignore X. In this case, we are at 5,681. So I'd say it's pretty safe to assume that we do not have to include that X in our calculation. Our Kb value is going to be equal to our products over the reactants. Remember, water is not included because it is a liquid. We can now plug in our values at equilibrium into this equation. So our Kb, 1.76 times 10 to the negative fifth is equal to X times X for the numerator. And our original concentration of the base, because we're no longer, we've canceled out our x. We've done our calculation to see that we can cancel it out. And so we can rearrange this. Equals x squared. We take the square root of both sides, and we find that x is equal to 1.33 times 10 to the negative third. Okay, so now we have to remember what x is, though. So x is our OH minus concentration. It is not equal to H plus in this case because we're a base. And so in order to find, we can find our POH. Our POH is equal to 2.876. And we can find our pH because it is 14 minus that value. In this case, 11.12. To find our pH of our basic ammonium solution. We know that this is correct because it is a basic. So now I want you to find the pH of morphine. So morphine is basic because it has a nitrogen in its structure. And so pause the video and see if you can calculate morphine's pH. Okay, so we're going to set up our ice table. We know our base concentration, 0 and 0, minus X is our change for the reactants, plus X for our products. And so I'm just going to double check real quick to see if we can ignore that X. So we're going to compare our concentration to the Kb value. And we end up with 937.5. So we can ignore the X. We're just going to ignore it. We set up our Kb expression. The base. Or conjugate acid, I should say, times hydroxide, divided by our base concentration. So we can 1.6 times 10 to the negative 6 times, just rearranging here, the base concentration times our Kb is equal to X squared. Take the square root of both sides. We find out that X is equal to 4.9 times 10 to the negative fifth. POH is the negative log of that value. Which is 4.31. And then pH is equal to 14 minus our POH. In this case, 9.63. And so our pH of morphine, 9.69.